Hello and welcome to this tutorial on time and celestial navigation. By the end of this tutorial, you'll have an understanding of time systems and their significance in celestial navigation. The advent of time systems based on atomic standard clocks and computer programs capable of instantaneous sight reduction has diminished the significance of solar, sidereal, and lunar time compared to their historical importance. Nevertheless, this time information remains extant in the maritime domain and continues to be published in the daily pages of the Nautical Almanac. Given their expert status, it remains pertinent for marine officers to maintain a comprehensive understanding of the astronomical factors involved in these time systems. This knowledge forms an integral part of their broader comprehension of the celestial sphere's mechanics. This video covers the following topics: the foundation of time measurement in celestial navigation is the Earth's rotational period. This rotation results in the apparent revolution of the celestial sphere relative to a stationary observer, causing celestial bodies to appear to cross and return to the observer's meridian once daily. A day is defined as the interval between two consecutive transits of a celestial body across the same meridian. While all celestial bodies function as timekeepers, some prove more practical than others. The Sun, despite not being a perfect timekeeper due to its variable apparent speed along the ecliptic, has been utilized for timekeeping throughout history, owing to its significant influence on terrestrial life. The period between two successive transits of the Sun across the same meridian is termed an apparent solar day. During one complete Earth rotation measured against a star crossing the observer's meridian, the Earth will have progressed along its orbit, altering its position relative to the Sun by a measurable degree. Consequently, for the Sun to cross the observer's meridian again, the Earth must rotate slightly more than 360 degrees. This additional rotation can reach up to 1 degree, depending on the Earth's position in its annual orbit. So, the Earth rotates through about 361 degrees during one apparent solar day. The situation is further complicated by the Earth's variable speed along its elliptical orbit around the Sun, moving fastest when nearest the Sun and slowest when furthest away. Thus, the difference is a variable amount both in quantity and sign. As a result of these factors, the apparent solar day does not constitute a time interval of fixed duration. The apparent irregular movement of the Sun, as observed from Earth, is manifested through variations in its apparent speed along the ecliptic. When this motion is projected onto the celestial equator, the hour angle of the Sun can be measured. As anticipated, this measurement reveals a non-uniform rate of change. Consequently, the hour angle of the Sun does not provide a practical unit of measurement. To address this challenge, while maintaining a connection to the Sun, astronomers have introduced a conceptual construct, the mean Sun. This theoretical body is defined as follows. The mean Sun is a hypothetical celestial body that is assumed to move along the celestial equator at a constant speed around the Earth. It completes one full revolution in the same time that the true Sun requires to complete one revolution along the ecliptic. This concept allows for a more standardized and uniform measure of time while retaining a relationship to the actual Sun. The mean solar day is defined as the interval between two consecutive transits of the mean Sun across the same meridian. During one mean solar day, the mean Sun moves westward from the meridian, completing a full revolution of 360 degrees in longitude over a period of 24 mean hours. The mean Sun's rate of travel is therefore 15 degrees of longitude per hour, so 1 degree of longitude corresponds to 4 minutes of time. This establishes an equivalence between angular measurement and time. This relationship between angular movement and time provides a consistent and practical basis for timekeeping and navigational calculations, overcoming the irregularities associated with the apparent motion of the true Sun. Local mean time is defined as the mean solar time observed at a specific longitude. Locations sharing the same longitude will experience identical local mean time. Local mean time at any given location is equivalent to the local hour angle of the mean Sun at that instant, measured westward from the meridian of that location, plus or minus 12 hours. This definition of local mean time prompts two considerations. 1. The addition or subtraction of 12 hours. This adjustment is necessary because the mean solar day commences at midnight, when the sun is at its lower transit of the observer's meridian. At this point, its hour angle is precisely 12 hours before or after its upper transit of the observer's meridian. 2. The equivalence of time units and angular measurements. While local mean time is expressed in time units and local hour angle in degrees, they are interchangeable due to the mean sun's rate of travel, which is 15 degrees of longitude per hour. This relationship allows for the common practice in astronomy and navigation of using hours and degrees interchangeably when discussing angular measurements related to Earth's rotation. Consequently, although local mean time and local hour angle are expressed in different units, they can be readily converted between time and angular measurements. Greenwich Mean Time is defined as the local mean time at the Greenwich Meridian. While Greenwich Mean Time has been largely superseded by the term universal time in scientific contexts, it remains a significant reference point in navigation. The concept of Greenwich Mean Time is intrinsically linked to the motion of the mean sun relative to the Greenwich Meridian. Given that the local hour angle of the mean sun is measured from the Greenwich Meridian, and the mean solar day begins at 180 degrees from this meridian, Greenwich Mean Time can be defined as follows. Greenwich Mean Time is equivalent to the Greenwich hour angle of the mean sun, plus or minus 12 hours. This definition establishes Greenwich Mean Time as a global time standard, providing a consistent reference for coordinating time across different longitudes and facilitating accurate navigation practices worldwide. Since all places on Earth are identified by reference to the Greenwich Meridian, longitude must provide the connection between local mean time at any place and Greenwich Mean Time. Consider New York as an example, situated approximately 75 degrees west of Greenwich. The mean sun, traveling westward from the Greenwich Meridian at a rate of 15 degrees per hour, covers this angular distance in 5 hours. Consequently, New York is 5 hours behind Greenwich in terms of time. When the mean sun reaches New York's meridian, its local hour angle is 0 hours, and its local hour angle in Greenwich is 5 hours, representing the time elapsed since the mean sun crossed the Greenwich Meridian. Similarly, when the mean sun completes its westward journey and crosses the Greenwich Meridian again, the local hour angle in New York is 19 hours, 24 hours minus 5 hours. It's important to note that this calculation may necessitate a date change in certain circumstances. This principle, using New York as an example, is universally applicable to any location on Earth. It leads to the following rule for converting local mean time on one meridian to or from the local mean time on the Greenwich Meridian, using longitude expressed in time. The concept of an imaginary mean sun, while enabling the use of standard timekeeping devices, introduces a complexity for navigators. This arises from the discrepancy between the timekeeping methods used for observation and the measurement used for observation. Navigators, when determining their position using the sun, measure the altitude of the true sun, which follows apparent solar time. However, their chronometers operate on mean solar time. To reconcile these two time systems, navigators must employ the equation of time, which is defined as follows. The equation of time is the difference between mean solar time and apparent solar time. The equation of time is not constant. Its value fluctuates in both magnitude and sign, depending on the Earth's position in its annual orbit around the sun. It reaches 0 and changes sign on approximately 4 dates: April 15th, June 14th, September 1st, and December 24th. The relationship between mean solar time and apparent solar time can be described as follows. Apparent time equals mean time plus equation of time. When the apparent time lags behind the mean time, the equation of time is negative. Conversely, when the apparent time is ahead of the mean time, the equation of time is positive. For practical navigation purposes, the value of the equation of time is provided in the Nautical Almanac. It is tabulated twice daily, indexed by Greenwich Mean Time. A shaded column in the almanac indicates a negative sign. These tabulated values require no further correction for use. A day is defined as the interval between two consecutive transits of a celestial body across the same meridian. While all celestial bodies can serve as timekeepers, some are more practical for this purpose than others. When a star is chosen as the reference point for observation, the resulting interval between its successive transits across the same meridian is termed a sidereal day. This distinguishes it from a solar day, which is based on the sun's apparent motion. For standardization and convenience, astronomers use the first point of Aries, also known as the vernal equinox point, rather than an actual star. Consequently, the sidereal day is defined as follows. A sidereal day is the interval between two successive transits of the first point of Aries across the same meridian. To measure angular distances in celestial navigation, a fixed reference point in space is essential. A point located where the ecliptic cuts the celestial equator serves this purpose. Ancient Greek astronomers identified this intersection during the spring equinox, which occurred around March 21st near the constellation Aries. They designated this point as the datum, naming it the first point of Aries, often abbreviated simply as Aries. Over millennia, the Earth's axial precession has caused a gradual shift in the position of this intersection point. Consequently, the first point of Aries has moved away from its namesake constellation. Despite this displacement, the astronomical community has retained the term first point of Aries to denote the vernal equinox, the spring intersection of the ecliptic and the celestial equator. This point continues to serve as the primary reference for celestial calculations, regardless of its current position relative to the constellation Aries. The autumnal equinox, occurring around September 23rd, marks the opposite intersection of the celestial equator and the ecliptic. This point is termed the first point of Libra. Like the first point of Aries, this is a defined celestial position rather than a physical star. As previously noted, the Earth rotates approximately 361 degrees during one apparent solar day, while it completes precisely 360 degrees during a sidereal day. The latter is measured relative to the transit of any distant star across the observer's meridian. The sidereal day serves as an accurate and consistent time interval. The apparent solar day, however, exhibits variations in duration throughout the year. Consequently, the numerical difference between the sidereal day and the apparent solar day fluctuates in both magnitude and direction. In contrast, the difference between the sidereal day and the mean solar day remains reasonably constant at approximately 4 minutes, which is the extra time taken by Earth to turn through the extra amount. While local sidereal time has limitations as a clock system, its significance as an angular measure is in determining a star's hour angle. The navigator's primary concern is not the elapsed time since the first point of Aries crossed the local meridian. Such a focus would necessitate a more complex analysis of the relationship between sidereal time and mean solar time, as these two systems diverge. Instead, by treating sidereal time as an angular distance, the navigator avoids this complication. The units of arc used to express local sidereal time are consistent and applicable for measuring the angular distance from the observer's meridian. In this context, local sidereal time is defined as follows. Local sidereal time is the local hour angle of the first point of Aries. While the Greenwich hour angle is tabulated in the Nautical Almanac for the Sun, Moon, planets, and Aries, to do so for all 57 stars used for navigation would produce an unacceptably large publication, running to several volumes. However, the Greenwich hour angle of a star can easily be found instead by adding the sidereal hour angle of the star to the tabulated Greenwich hour angle of Aries. We'll explore a numerical example in the next segment. The local mean time of a star's meridian passage is frequently required for two primary purposes: to verify the corresponding date at Greenwich and to determine if a specific star will be on or near the meridian during twilight hours when a suitable horizon is available for observation. The following principles are essential for understanding meridian passage calculations. Greenwich hour angle is measured westward from Greenwich. At meridian passage, the star must be situated on the observer's meridian, and the star's Greenwich hour angle must equal the observer's west longitude. An east longitude can be converted to west longitude by subtracting it from 360 degrees, resulting in a value exceeding 180 degrees. The following equation holds true at meridian passage. Observer's west longitude equals Greenwich hour angle Aries plus sidereal hour angle star. To calculate the local mean time of meridian passage, rearrange the equation to solve for Greenwich hour angle Aries. Convert the resulting Greenwich hour angle Aries to time using the incremental tables found in the Nautical Almanac. Adjust the obtained Greenwich mean time for the observer's longitude to derive the local mean time of meridian passage. When deciding on a suitable star for a meridian observation, it is necessary to limit the choice to that star whose meridian passage occurs during twilight hours. Nautical twilight is defined as the period when the sun is between 6 degrees and 12 degrees below the horizon. During this interval, bright stars are visible and the horizon is sufficiently clear for stellar observations. It is possible to obtain good star sights at times both earlier and later than those falling within nautical twilight. Procedure for identifying a suitable star for meridian altitude at twilight. 1. Obtain Greenwich mean time of nautical twilight. 2. Obtain DR longitude for this Greenwich mean time. 3. Calculate local hour angle Aries. 4. Subtract local hour angle Aries from 360 degrees to obtain the sidereal hour angle of an imaginary star whose meridian passage occurs precisely at this time. Sidereal hour angle star equals 360 degrees minus local hour angle Aries. This equation is derived from the following relationship at meridian passage. 5. Consult the list of stars in the Nautical Almanac and identify one or more stars with sidereal hour angle values similar to that of the imaginary star calculated in step 4. Consider magnitude and altitude when making this selection. 6. Calculate the local mean time of meridian passage for the selected star and compare this time with the time and duration of twilight determined in step 2. 7. Assess whether a meridian or ex-meridian site is feasible based on the comparison in step 6. 8. Prepare for observations by pre-calculating the meridian altitude of the selected star and noting the time and altitude of meridian passage. Meridian passage occurs 18 minutes after the start of nautical twilight. Depending on the horizon available, either a meridian altitude or ex-meridian altitude should be obtained. The meridian altitude should now be calculated or found by inspection from suitable tables. If two successive transits of the moon were observed across the same meridian, the interval between them would be one lunar day. Since the moon itself is describing an orbit around the Earth in the same direction as the Earth's spin, the interval between the two transits of the same meridian would be longer than the mean solar day. At the diagram, A1 is a measure of the mean solar day, but while the Earth has moved from A to A1, the moon has reached C, and so the Earth will have to turn through a further angle approximately equal to B1, A1, C, before it is on the observer's meridian again. The time taken to turn the extra angle B1, A1, C averages 50 minutes. It is not necessary, however, to work in lunar units to find the hour angle of the moon, since Greenwich hour angle moon is tabulated against Greenwich mean time in the Nautical Almanac. The Synodic month is the interval between two successive new moons, when the moon lies in a straight line between the Earth and the Sun, and therefore appears black. This lunar cycle is crucial for understanding and analyzing tidal patterns. The moon makes one complete revolution about the Earth in 27.32 mean solar days. This is a sidereal month. But if the moon were a new moon at the beginning of this period, it would not be a new moon at the end of the period, because it would not lie in a straight line with the sun and the Earth. To achieve this position, it must move along its orbit round the Earth, and while this is happening, the Earth continues along its own orbit round the sun. A further 2.21 mean solar days elapse before the moon is again a new moon, resulting in a synodic month of 29.53 mean solar days. As previously stated, during one lunar month, the Earth completes approximately 29.5 rotations relative to the sun. However, due to the moon's orbital movement during this period, it crosses the meridian only about 28.5 times. This phenomenon accounts for the 50-minute discrepancy between the mean solar day and the lunar day, as demonstrated by the following relationship. 28.5 lunar days equals 29.5 mean solar days. Therefore, one lunar day equals 29.5 mean solar days divided by 28.5, and one lunar day is approximately equal to 24 hours and 50 minutes of mean solar time. This extended lunar day explains why we observe the moon rising and setting approximately 50 minutes later each day, on average. When the sun is used as the celestial reference point, solar time results. If the actual sun observable in the sky is used, apparent solar time is involved. And if a fictitious mean sun is used to provide a time having a constant rate, mean solar time results. Time reckoned by use of the first point of Aries as the celestial reference point is called sidereal time. Use of the moon as the celestial reference point provides a lunar day, the basis of lunar time, which is useful in tide analysis. Since the various celestial references are in motion with respect to each other, as seen from the Earth, apparent solar, mean solar, sidereal, and lunar days are of different lengths. If the meridian of the observer is used as the terrestrial reference, local time is involved. If a zone or standard meridian is used as the time meridian for mean solar time over an area, zone or standard time results. Use of a meridian farther east than would normally be used, so that the period of daylight is shifted later in the day, produces a form of zone time called daylight saving or summertime. Time based upon the Greenwich meridian is called Greenwich time. Greenwich Mean Time is of particular interest to a navigator because it is the principal entering argument for the almanacs. Mean solar units are customarily used to indicate time intervals. The smallest unit normally used in celestial navigation is the second, but in some electronic equipment, the millisecond, microsecond, and the nanosecond are used. Time of day is an indication of what part of a rotation of the Earth has been completed. Thus, at midnight, the day begins, and 12 hours later, the Earth having turned through 180 degrees. Understanding the relationship between Earth, the Sun, and the stars is not merely of historical interest. It remains a crucial skill for modern navigation. While advanced technology has revolutionized navigation, understanding these celestial connections continues to be essential for marine professionals. This knowledge not only serves as a reliable backup when modern systems fail, but also deepens our appreciation for the vast universe around us. Gazing at the night sky offers more than just celestial beauty. It provides a tangible link to our rich maritime heritage. The same stars that guide today's sailors have illuminated the paths of explorers for centuries, creating an unbroken chain of human wayfinding across time. This enduring connection between humanity and the cosmos evokes a sense of wonder and perspective, reminding us of our place in the universe. In essence, celestial navigation is more than a skill. It's a bridge spanning our past, present, and future. It reminds us that even in our high-tech world, the timeless beacons above still have the power to guide us home. So the next time you look up at the night sky, Remember, you're witnessing the same celestial map that has guided humanity across oceans for millennia.